Did you receive chapter 7? You have chapter 7. And also you will receive this morning for another small section, which is a part of really 5.3. So it's a general expression for DAA1, which is first order, the doubly asymptotic approximation. The idea is not to fully understand whole math, but the direction for how to get to the general solution for general kind of type or configuration of structures. Okay, so I displayed this about third time. The problem is when I start for particular topics, I really must have finished that hour. Otherwise, now, last Friday or last Wednesday we started around the end of the lecture. Then Friday, again, pick up and go through once again. Otherwise, it's very easy to get lost. So once you get lost, then nothing is good. So I want to finish this today. Infinite plate, generalized infinite plate. I want you to understand this, to understand a really good concept on the fluid structure, the interactions. So then today I will of course assign the water situation, and then I will do the generalized spherical shell problem. Then I want to get the feel of it, because the spherical shell problem is a lot more difficult in math, but it's very much doable. It's a lot of operation, math operation you have to do, but we can really allow us to go through all the way to the end. And when you return, I want you to sit down, really drill through. My notes are so detailed so that they need to really go through and check it out. Okay? Then after that, I think if I finish that today, I think that's good. And Wednesday, I'm going to give you so-called general DAA1, which means first order doubly asymptotic approximation. What does it do? What is it good? What the application would be? What has been done in the past using DAA1 or DAA2? What's the trend at the present times? What direction we must go? Things like that. To perform the underwater vehicle analysis subjected to shock situations. Okay? So then you will catch what's going on. The computing capabilities moving so fast. It's just so fast, unbelievably fast, and everything is changing, and computational scheme is changing. And then you have to get along with that. You can't stick to all the scheme. Then, of course, this week, maybe starting Wednesday or Friday morning, I'm going to start looking into the chapter 7, which is shock qualification. So shipboard equipment, to look into detail, then I'm going to really look what's going on and get down to how to handle the shipboard equipment against the shock. very important. It's two different kinds you have to understand. One is the structure dynamics problem for the whole ship system. That's one thing. Or how the ship structure could get affected by the underwater shock. And the second stage is, idea is nowadays, of course, it's not to kill the ship. When I say kill, sink the ship. That's not the idea. Idea is to paralyze the shipboard equipment, all the computing system, all the computers in the ship, every piece of weapon systems, there is a chip, there is a computer implemented in there, and inside the computer there is a chips, CPU processors. So if you kill the chip, that's the end of it. It's a sitting duck. Ship is a sitting duck, go nowhere. All the weapon systems you can operate. Even if you can operate, it can't really hit properly because all the weapon systems has been damaged. That's the idea. That's the idea, not the busting ship, not sink the ship. That's the current trend. Of course, in China naval ship, you saw it's split into two pieces. That's the basic, the mechanism. You know how it happened. You all know that. You all know that fully by the underwater shock pressure plus. People know, everybody knows, even the mothers, little children. Oh, that's by the bubble jet. Everybody knows the bubble jet. I didn't know the name bubble jet before, but now Korean people, they invented the word, the bubble jet. Yeah. Bubble jet. Jet flow by the collapse of the bubble. Simple word, bubble jet. And that name has been used when we were out in Orlando last month. Few papers talk about the bubble jet. Name is a bubble jet. So it's really, really nice. And now, from end of this week, toward the end of this week, or starting whenever this week or the next week, then you will learn the shop qualification for shipboard equipment. For example, I think I might mention to you already. Nowadays, it's really, I got the same kind of the coughings of the weekend. What I was wondering, sometimes difficult kinds of. Oh, anyway, for the shipboard equipments, you have to know one approach, which is called the DDAM, Dynamic Design Analysis Method, DDAM. But that's the way the U.S. naval technology employed since 1960s. It's time to update, and we are doing it because all the transient computational analysis is one of those. But for simplicity, DDAM is the way they really check out whether the shipboard equipment is going to survive or not. You see what the name is interesting. Simple calculations. Not making million degrees of freedom system. So Willis, when you go back to Singapore Navy, If they try to make a 1,000,000 degrees of freedom model for shipbuilding equipment, what you're supposed to say? That's no good. That's not, the D-Land is not intended to solve the 1,000,000 degrees of freedom system. Maybe 100 degrees of freedom system, up to 100 degrees of freedom system. And I want you to get the idea. This idea I learned since I was young, like yourself, to make it more perfect model, for example. I really make a detailed model. I involved, at the age of 30, nuclear power plant design, the whole design of the nuclear power plant, including reactor, steam generator, whatsoever. And it's good, the model was good, I checked it out, it's good. Then I put it in the computer, Friday, go home. I think I mentioned to you, the month before. Then it keep running and running. That's a year. That's a year before you were born. It's 1973. It keep running and running. Of course, computer is slow that time for years. And Monday morning, when I came back to work, oh my gosh, they were looking for me and all that before they killed my job because didn't finish. You keep running and running and running like forever. So 8 o'clock in the morning, all the other programs they have to run. So they killed my job. They didn't fire me. They could have fired me because spending the computer time all 2.5 days, I was lucky not to be fired. That slow. So nowadays computer capability we have is so fast. Still complain. I need 1 terabyte storage. 1 terabyte. You know how much 1 terabyte is? 1,000 gigabyte. You know what's 1 gigabyte is? Gosh, it's unimaginable. In '85, when the first the IBM put it out, the PC, that came after the Apple. Then what I had was the whole thing, including memory, hard disk, everything is 200 megabytes. That's a superb, that's a big, gigantic storage. Now, this piece holds how many gig or meg? This holds 4 gigabytes. So we are living in this era. It's scary. So I want you to think big, always big, looking forward, and set your dreams, and get your own creating sort of the space, virtual space. And I want you to work on it, gusto, right? And when you go back to your country, then dream. You have to make it come true. That's that. Think big, not just to think small. That's the usual stuff. Okay, so this equation set, we all did this, and here is one I'm going to be right over here because I move all the way to the end. Okay. So U is equal to minus LP And what else? This is equal to U is equal to minus LP over LX, or I wrote about 4 times. Oops. This is functional. Did I do SQ? It's a basic definition of the velocity potential. And P is equal to PXT, of course. PXT is equal to rho naught P XT, which is equal to P is equal to rho naught LP over what else? And P double dot XT is equal to C naught square P double dot. Of course, this is same form as the wave equation. I think that's one of the 3 most important things. Governing equations, and initial condition we did, okay, and boundary condition, boundary pressure, that means pressure at the surface of the plate, which is Pi, incident shock wave pressure, plus PS, which is scattering wave pressure. Scattering wave pressure include reflection wave plus the pressure due to the motion of the plate. And solution phase, we are using wave propagation solution. P is equal to Pi plus PS. Pi is incident, the wave velocity potential. S is the scattering wave velocity potential. And now this is important here. In the defining process, the Pi is equal to psi L, which is defense department. I don't know why they're always. Okay, so that don't forget. PL means wave is moving what direction? Opposite to the positive x-axis, right? Yes or no? Yes, because the sign is a plus sign there. So plus sign right here, plus sign. If it's negative sign, then that's the same direction as the wave move in the same direction as a positive x direction in chapter 2, and plus means opposite direction. So this is to the left. Left means in this case is the direction, negative x direction, right? So where the shock wave comes through, negative direction, and this is to the right, so which means it's like a scattering wave after reflections, things like that. So if you look at carefully, as I explained already, it's straightforward using these 3 basic principles. So scattering wave pressure at x is equal to 0, what does it mean? Right on the face of the plate, right? So this is really for boundary pressure. So after that, you just put this as a, that's what we derived this before, then substitute this arbitrarily the psi functions right in there. So this scattering wave is what direction it moves? To the right. So to the right is this expression, which is psi r. Psi r. So after that, you use a chain rule, then you got that. So it's very similar. All the pressure, scattering wave pressure or incident wave pressure is all the same approach. Whether it's infinite, generalized infinite plate or the spherical shell problem. So you can, I want you to still go through when you return to your office there. And now it's a scattering wave, the plate surface, the interaction relation. So US is equal to this, which means US is minus del V, S over del S is right here. Right. And same way, US minus del over del X, then psi R. This is to the right, of course. Then you just go through exactly the same way. Then once you find here is PS is rho naught C naught US. This is very logical. You didn't assume anything. You didn't assume anything, but PS, usual problem is in front of this, whether it's positive or negative. But this makes sense. Using infinite plate, you can really tell very easily. This is the scattering wave pressure. It's moving to the right, right? So same direction as US, which is fluid particle velocity, right behind the scattering wave pressure. So this is one equation you can tell. By the same analogy, I can write the PI is equal to rho naught, C naught, maybe UI. We know this is a pressure. What about the sign? This is moving to the right, which is a positive x direction. This is just for analogy. Analogy. So we know this, then my question is, of course we will really derive it, but can you tell whether it's a positive or negative? You have a choice. 50% chance for winning. This is going to be negative. Why? Because UI is the fluid particle velocity behind the incident shock wave, which is moving to the left. Left is negative x direction, so I can tell right away by this analogy, this guy gonna be the negative. But of course, we're gonna look at that. Got it? So now the surface pressure, which means at x is equal to 0, P is equal to Pi plus PS. Pi we know. Problem is PS, the scattering part we don't know, which is caused by the motion of the plate. So this is PS is rho C naught US right here. Then now you substitute this into equations of motion. So then you have, you just plug in this guy into here. or US is W dot minus UI. I just plug in. W is of course unknown. Okay. Then which is right here. So rho naught, C naught, W dot move to the left. You have this equation. And this two line I spelled out, derivation is in the next page. Pi is rho naught, Pi dot. We can tell because it's a Pi relevant to Pi, which is right here. Then expression for Pi is to the left. So psi L comes the picture. So psi L, if this is right, then you can put this expression, this star is del psi L over del. This notation, simply speaking, this is the transport part between the station. After you got the relation, this side business is all out. Just used as a math tool to solve the problem. Okay? Right. And this relation, you know, this relation is right here. If you plug in the psi L into here, this is time derivative, you end up having this. So psi L star is C naught minus C naught times UI. Look at carefully here. Then if you plug in that expression right here, is Pi is equal to rho naught C naught times UI. So it's a minus, right? Two lines, right? Psi L star is equal to minus times C naught times UI. You plug in here, then Pi is equal to rho naught minus rho naught C naught and UI. Visualize. I'm really encouraged to visualize the equations. You can figure out in your brain quickly and keep practice, but it will help you tremendously. Then derivation coming right here. UI. It's just the same approach, nothing new. Then Pi is equal to minus rho naught C naught U. As we saw this here, PS, Pi, without the derivation you can tell. Because approach is the same, mathematical is the same. Then equation 13, plug in equation 12 over here. Then you end up having, this is 2Pi. And the QT is what? That's internal pressure, right? Which is moving to, which is applied to the right positive. This is a minus. Why? Because Pi business is moving to the left. So it's a minus. Minus 2Pi. So if there is no internal pressure, you drop the P. And in this case here, for your nomenclature, for positive x direction to the right, this is negative. So watch out always for the sign, positive and negative. So otherwise it's quite good. This is going into the boundary pressure, and we'll look at the pressure component. This is at x is equal to 0. Then Pi plus PS. PI is incident shock wave pressure, and PS is of course scattering wave pressure. Scattering wave pressure has two components. Okay, one is reflection wave, which is same as PI, plus the PS, that's really scattering part, which is really pressure caused by the motion of the plate, simply absorbed by the plate. So, which means rho naught, C naught, W dot. Then, if you plug in the equations of motion, you have this. What's going on? This is 2pi, of course, 2pi, and this is the radiated pressure, which is caused by the motion of the plate, or 2pi plus this. Clear, isn't it? No confusion, very clear. So now I solved the easier one. One side is water, the other side is air. So now is your time, your turn to solve the same for water situations. Okay, most of the things are same. So when you do the homework, it's a homework. I think homework, some homeworks are due today, isn't it? Return in that request. And you can still, as a practice, I want you to write the same procedure as I have done here. Okay? But the only difference is you have a transmitting shock wave. Right? So, same thing, only difference is you have incident shock wave. You have plate, water. You have incident shock wave. You have scattering shock wave. And you have transmitting shock wave. If it's air, you don't have a transmitting shock wave, right? Because it's air. Air, it's just impedance difference is too much. So very small compared to water. You don't have to count anything transmitting into the air. This is you should use. I want to see how to handle PP. That's the main thing. But you know the answer. Answer is, for the equations of motion, you have before, you have rho C, like a W dot. This is for the case with the water one side. If this water is a two side, you have two there. You know the answer. I'm just giving you an answer. You have to prove it. Okay, any questions? Approach is very clear. Then you have to get in March. Math is very clear. Now the spherical shell wave. It's a sphere. You have air inside the spherical shell. It's like a soccer ball. It has a shell scheme, and inside is air. So of course it has a weight there, mass of the shell. When you drop into the water, it could be neutralized at a certain depth in the water. Okay. Okay, then apply the shock situations. Okay. So here, the coordinate is concerned. This is point symmetric, and this is a positive R direction. It's a spherical coordinate. How many different variables you need? Like a spherical coordinate, you have R, theta, psi. But point symmetric, so you don't need a psi or theta, things like that. And loading, this is a Q. Loading from inside toward outside is internal pressure. So that's a positive direction. This is a positive direction. And the water is surrounding the spherical sphere. Okay? And the radius of the sphere is A. And rho C is for the water. What else? And this is really idealized plane such that you have a shock. So this is all of this notation. This is a shock. I'm going to call that as a converging shock. Converging. This idealized shock situation. Okay? Converging shock is converging toward the center of the sphere. The center. And the shock wave, which is scattered after it hit the shell, it will scatter, which is what you could call such a wave? Diverging wave. Okay, it's converge and diverge. So I just use that word, converging. Wave which comes to the center, converge. Converging wave. Diverging to the center, in all after it hit the shell surface, is going to all converging. I'm sorry, diverging. Diverging. Diverging wave. Heading, then converge, which is a scattering wave. And of course, we are dealing here is mass per unit area. You could think of the stiffness springs per unit area and damper in the unit area, Q per unit area, things like that. Shell thickness you could define as H, like a uniform shell. Configuration is clear. And the equations of motion, as before, very clear. M W double dot B W dot A W Q minus P R equal to A and T. Because the radius of the shell is concerned to get the pressure right at the surface of the shell. We have to compute for R equal to A. A is the radius of the shell. So this is minus what? Incident to shock wave pressure is converging to the center positive x direction is in the radial, outward radial direction. So the direction of the PI is inward directions, right? This is minus. So now everything is all good. This is simple, similar equation for the infinite plate. So PAT is total pressure acting on the plate in the minus R direction. Of course, that's unknown. P is unknown because there is what part? Scattering part. That is there. That's unknown. Boundary condition. Boundary condition. What does it mean, boundary condition? Right at the interface, right, between the water and the shell, at R is equal to A. No gaps. Motions are normal to the shell. Always when you have a curved shell, you're dealing with the component normal to the shell at any particular point. Okay? Normal component is what you are always looking. So in this case, for the spherical shell, normal direction is always in the radial direction. No gap assumption. All the equations derived through here, when cavitation occurs, the theory is no good. Cavitation occurs because cavitation occurs means there's the gap between the water and the shell. But it opens due to the flexibility of the shell, then it closes right away. It doesn't stay long at all. Instantly closes. Whenever something closes, what happens? There is always sharp pulse in general. Right? So yes. So no gap, but so close when you have any other situation to put that in, you can just use it as even for local cavitation situation. If you stay long, you can, but it's instantly. P is equal to rho naught P dot. This P dot is simply del P over del T here. Okay? And this is a definition to define the velocity potential set. Very similar situation. Instead of x is r. So it's a spherical coordinate come into picture. And the wave equation forms here. This is the differentiation with respect to time. But this guy is due to the differentiation with respect to the r twice. Then it's a spherical coordinate. It has a two term. Third term, fourth terms are related to the other two coordinate axes, like theta and psi, or phi. So phi double dot has a two term. This n has to be moved down. Okay. So that relation, this guy, that guy is right here. No differences. So exactly the same approach, okay? Initial conditions, that means what happened for t is equal to 0. So when t is equal to 0, phi is r comma 0. which is not 0. What happened? If this is, for example, phi s r comma 0 is equal to phi r comma t is equal to 0. Initial condition is that's not 0 because phi relate to pi. Pi is not 0 at t is equal to 0. But ps, the scattering component, scatter the phi, is 0 at time t is equal to 0. The scattering part is in deep sleep. Right? But scatter, there has to be the term which will really start dancing when incident shock wave has done something. So PS at t is equal to 0 is 0. But anyway, this condition is initial condition, and W and W dot is equal to 0. What does it mean? Initial displacement, initial velocity is equal to 0. You can, if you want, you can set up the initial deformation as a non-zero. That's okay, right? I said as in this case, everything is all natural. It is all calm. Horizon is beautiful sunset. Then it's ready to have dinner in the workrooms, and bang! And then, you know, there's no dinner. We're supposed to have a movie in there. No movie. Is what do you call that? Such a the drill for emergency situation? Quarter. I don't know the name. We should know the name. General quarters, GQ. In U.S. Navy, they say GQ. General quarters. Then everybody is running to go back to the position to start the mission. All the visitors from Naval Postgraduate School, about 10 people, we have to go hide in the cabin and stay in the cabin. Oh, some experience. Okay, boundary pressure. Boundary pressure means pressure right at the surface of spherical shell, right? Pi, PS, always is the same. No differences at all. It's not same, it's all symmetry. And now, this is the part. Identical process. This is the Pi. Let Phi is equal to 1 over R. Before the spherical wave, it was 1 over R times arbitrary function F, right? Then was T, in this case is incident shock wave. Incident shock wave is converging opposite to the positive R direction. So this sign has to be plus, right? Yes. And this term was X over C before. But in this case, it's R over C minus A over C. Why? R should be greater than or equal to the A. If R goes inside the shell, then that's not valid. So it has to be, R has to be greater or equal to the A. So this is R. So R is concerned has to be greater or equal to A. If it's not, it has to come inside the sphere, which has no interest at all. So this is what the situation to avoid. The R is greater or equal to A. This is a plus because it's a converging, means in the infinite plane we use what? L, right? So here C converging, D is diverging out. Same direction as a positive R. So it has to be negative here, diverging. For the VS, scattering from the surface of the shell. Make sense? Makes sense. So this, in the defining this, you have to be careful. I'm not going to bother to assign the homework problem. Inside of spherical shell is the water, outside is the water. You will do for the infinite, generalized infinite plate, that's enough to capture all the essence of it. But this case is a little more complicated. So I want you to just sit, after you return, sit back, really read through, all right, derivation as you please. Create a propagation solution. So Phi incident wave velocity potential. Same thing. Ps scattering wave velocity potential. We need to employ Laplace transform. What's the purpose of using Laplace transform? John, what's the purpose? No. What's the purpose of using Laplace transform? Louder. Transfer domain, of course, from physical domain to Laplace domain, of course. So no, when you employ Laplace transform to solve the problem, just for fun, so you are the winner for second the middle terms in. So what's the purpose? No. Well, at least what's the purpose? No. Son, we convert differential equation to algebraic equation to solve. So the microvibration force, they throw into the plus domain. Why? To solve differential equation is a lot more work. I want to throw into the Laplace domain, then I can solve simply algebraic solution in the Laplace domain and throw back, take the inverse Laplace transform to get the solution in physical space. Always when we have a transform, it has a reason. That's why Laplace transform, even there's a book, big book, which has all the Laplace transform of the given function. I have one copy, I don't know whether I brought the to Korea or not. In book, you look at Laplace transform, then you don't have to derive all of that. Just look at the function, then look at the Laplace domain transforms. Okay.